Okay, if you can grab your chair, we'll get started here so we can get out of here at a decent time. As you can see, it's already 2 in the morning, so we got to get going. First thing, I want to congratulate last year's officers, Sam as president and vice president. I don't see, or Robin, I don't see here as secretary. And we had Tom Roth, Peter Taherna, and Stephen Kennedy for being directors. They did a great job. Hopefully the new board can continue on. You as well. Next slide. All right, do we have any visitors today? Yes. So how'd you hear about us? Online, good. Any astronomy background from before?
Always wanted to be an astronaut, and I just picked it. I think I started looking 5 years ago and learning. I have an Orion 4.5, but I have a C-Star S50.
Well, welcome. We'd love to have you be part of the club. Anybody else? Visitors? Or are you a new club member? Yeah. All right, next slide. I want to welcome our new members. Garner Buchanan. There. Ahmad Karimi. No. Roy Reynolds. And Mark Mayath. I know you're there. Okay, I met you. Welcome back. We didn't scare you away yet, so that's great. What kind of scope are you using right now? Well, good. Glad to have you at the club. Next slide. All right, some background on the Fort Worth Astronomy Club. We were founded in 1949. We got 420 individual members, which is 25 family or single family member accounts. We have a wide range of experience, from visual, astrophotography, you name it, in between. All of us are willing to help you on your journey. You got questions on stuff, we're here to answer questions for you. If we don't know the answer, we'll make it up. We'll help you out. So, we're a nonprofit organization, so please feel free to make donations. See Constantine about that. So, next slide. All right, our mission is to promote astronomy via public outreach, encourage and support groups interested in astronomy, cultivate observing and research among the members, and promote the building of astronomy instruments and make club equipment available to members. And I'm going to talk about that a little bit later on what we're doing there. Next slide. Resources, we have a member's handbook we give out to you. We have a Thompson Observatory south of us that we can use. We have our own Rising Star observing area. We're going to go through a little bit on that tonight. We have a bunch of club ice telescopes and eyepieces. We have about 51 scopes out there that people can use. And we're looking at some other loaner programs and stuff out of that. And we have our online presence, Facebook, YouTube, all that. Next slide. Forgot I'm being taped. This is the Rising Star observing area. We have an astronomical building, got a couple of bunkhouses, got a lot of our scopes in there. We got lease pads and club pads. They all have electricity. We also have Wi-Fi that shoots down there, so you can sign in and be online. There's also Cat 6 cable into all these, so you can hook into the internet on the pads itself. Got an RV parking area. We got a maintenance building over there where we got our lawnmowers. And we have a compost toilet in this little green building. Next slide. So you see we got a variety of Dobsons, refractors, Schmidt-Cassegrain, and a couple of solar scopes as well. So we have all kinds of resources if you need to borrow something or use it or just go out there and have fun with us. Next slide. These are our presence online, Fort Worth Astro, our Facebook, our YouTube, our groups IO. So You have to specifically sign up for that, but it's kind of like a message board back and forth. Not everybody signs up for that, but if you want to know, hey, is anybody going out to Rising Star tonight or over the weekend? That's where people share stuff back and forth. The groups, and then we have a separate part for APSIG, which is our astrophotography special interest group. A lot of stuff going on that, and Robert back there is running that for us right now. And then we have a Zalza store where I have a merchandise, and we also have a new one called Big Frog. We'll talk about that in a little while. In fact, that's a Big Frog t-shirt right there. He's got, and I got a Zalza one. So, next slide. Additional info can be found at our info. If you send that email, Constantine and I get that email. We'll answer your questions. And you can join our club right online right there. Next slide. That was quick. I'm going to hand it over to Bill, who's going to introduce our speaker.
Later. Thank you, Sai. So, I am happy to introduce Dr. Zheng. He's at the Department of Physics and Astronomy at the University of Utah. I'll speak up, thank you. And he studies cosmology, large-scale structure, galaxy clustering, and what he's going to be talking about tonight is gravitational lensing. So if you don't know what that is, think Einstein's cross, and you'll learn more about that tonight. So please help me welcome him.
Thank you. Can you hear me well? Okay, so I think I need to share my screen. So somebody need to make me share my screen. Okay, good. Let me see. Can you see my screen? I haven't. Can you see my slides? Okay, it's a single slide, right? Not the presenter's mode. Okay. Thank you. Thank you for the invitation and thank you for the introduction. So today I want to share with you something like I think is really fun to learn, and also I also have been doing work really related to this kind of field. So I will talk about nature's biggest telescopes. So this is related to a phenomenon called gravitational lensing. So I will tell you what this phenomenon is, and give you a brief history of this gravitational lensing, for how the gravitational lensing got proposed, how the gravitational lensing got observed, and then I will just showcase the applications of the microlensing for us to learn about the universe. I will focus on a few of these applications. I will talk about macrolensing, what macrolensing is, what we can learn from macrolensing, and strong gravitational lensing by galaxies and clusters, and weak gravitational lensing by galaxies and clusters. Finally, I will end with the so-called cosmic microwave background lensing. I don't know what typically you do. Please feel free to interrupt me, and if you have any questions, and you want any clarifications. Okay. Gravitational lensing. To talk about the gravitational lensing, we need to think about gravity or gravitation. So Newton had this famous law of universal gravitation, and then Einstein basically kind of upgrade this theory, and Einstein developed his theory of general relativity, which is the theory about gravity. Okay, and gravity is caused by curved space-time. So in Einstein theory, one of the key prediction or key results from this general relativity is that light can be deflected by the gravity of an object. For example, this object could be a star, could be a galaxy, could be a galaxy cluster. Okay. So the light travels no longer follow the straight line, but travels kind of like along a deflected line. Okay, this kind of get deflected by the object. So in that sense, if light can be deflected, so this object, you can think this object acts as a lens. Okay, so we know this kind of we are familiar with this lens, like for example, this convex lens. The light can be focused. And similarly for object, the light can also be deflected and can be like some kind of like focused. Okay, so these kind of things can produce a lot of interesting effect. And in general, we call this phenomenon gravitational lensing. Okay, the main effect of gravitational lensing include this, like the gravitational lensing. If we have like object, like act as lens, there's like a background sources, and the image of the background sources can be distorted. Okay, that's one effect of gravitational lensing. And the brightness of this background source can also be changed because of this gravitational lensing, this focusing effect. Okay, and also, if I have only one source, the one source can be, this kind of gravitational lens can produce multiple images of this source. That's another effect. These multiple images, this kind of like when the light travel to us, these multiple images, they may have different time delays. So that the images, if there's a change in the image, we may not observe the change at the same time. There will be some relative delay. Okay, that's like all these effects are all relevant for gravitational lensing. Okay. So in terms of the history of gravitational lensing, so I mentioned, so that Einstein developed a theory of general relativity. In fact, long before his development of the theory, basically he spent like 10 years from 1905 to 1915 to develop the general relativity, this theory. So at sometime before the full theory, he started to think about what the behavior of the light in the gravitational field, based on his equivalence principle. Okay. In fact, in 1911, Einstein already predicts that the light can be deflected by the gravitational field of objects like the sun. Okay. And at that time, in fact, his calculation of the deflection angle is wrong by factor 2, and this factor 2 is important. In fact, if you apply Newton's gravitational theory, you can also some kind of like can calculate the deflection angle of the light, and but Einstein's calculation in the end, the correct calculation would have a factor 2 larger than Newton's calculation. Okay. And then in 1912, after the prediction of the deflection of light, Einstein basically wrote a note on gravitational lensing. I start thinking about the gravity can act as a lens. Okay. Then like in 19 in this note, here is the basically Einstein's notes on gravitational lensing. In fact, this note is pretty like clear, and a lot of these notations, equations, basically is just the equations we used today. Okay, essentially, maybe with some change of symbols, but essentially we are using the same equation to study gravitational lensing. Okay, that's like more than like 100 years ago, Einstein already like start to write down the basic equations of gravitational lensing. Okay. So after Einstein developed the full theory of general relativity, and he made one of the major predictions of the theory is basically the deflection of light. And then a few years later, in 1919, this famous event, there's a total solar eclipse, and Sir Arthur Eddington, so he basically tried to observe this and try to confirm or test Einstein's prediction. The idea is basically during the full eclipse, the position of the star near the sun can change due to the deflection of the light caused by the gravitational field of the sun. Okay? Here is the illustration. So if the sun is not there, so the star's position will be indicated by the yellow point. But because of gravity of the sun, this deflection of the image will look at to a different direction. So there's a small shift of the position of the background star. Okay, And Eddington basically measured the shift. And the result agreed with Einstein's prediction. So this basically is the year that make Einstein really famous in terms of his development of the general relativity. That's what happened in 1919. Okay. And then there are some following this kind of this test, this kind of discovery. So Eddington also started to think about the gravitational lensing effect. Said, okay, if it's possible, there's multiple images of the background star. If, for example, the sun. So deflected kind in one side of the edge of the sun or the other side. So there can be two images that is study. And then about 4 years later, Schwarzen mentioned, okay, so if we have perfect alignment of the observer, the sun, and the background star, so instead of forming two images, because there's no preferred direction, no preferred position for the light to be deflected. Instead of seeing two images, we will see a ring. So this whole background source will appear as a ring around the sun or around the star. Okay? So this is now we call this kind of phenomenon, this ring, called Einstein ring. Einstein ring is a really important concept in gravitational lensing. Okay. Just to make sure that can everyone see my cursor? Okay, great. Thank you. Okay, then in 1936, finally there's a paper about gravitational lensing. Einstein published a paper in Science. It's called the lens-like action of a star by the deviation of light in the gravitational field. So if you read the paper, you can see, okay, so this is totally caused by an amateur scientist who visited Einstein. At that time, Einstein was at the Institute for Advanced Study in Princeton. So you can see, okay, the beginning of the paper, some time ago, this guy Mendel visited Einstein and pushed Einstein to publish this calculation about gravitational lensing. Okay? So basically, Einstein wrote this paper upon the request of this amateur scientist. And in his letter to the editor, you can see what Einstein wrote. So very frankly, so let me also thank you for your cooperation with the little publication, which Mr. Mendel squeezed out of me. It's of little value, but it makes the poor guy happy. So that's how Einstein view this publication. And in this paper, you can see also in the conclusion mentioned, okay, therefore, there is no great chance of observing this phenomenon, even if dazzling by the light of the much nearer star, something like that, okay? And that's basically Einstein's thought. Einstein, in fact, Einstein this time, he was wrong. Okay, and now this gravitational lensing has become really powerful tool for us. Okay, but this is basically the first paper to really discuss gravitational lensing and to do the calculation of gravitational lensing upon the request of amateur scientists. Okay. So following this paper, there's some theoretical development, but only after 40 years later, more than 40 years later, we start to observe gravitational lensing. Okay, the first observation or discovery of gravitational lensing, that's in 1979. Okay, by Walsh, Caswell, and Weinman. Okay, so the title is basically discovery of double images of gravitational lens, the quasar. Okay, so quasar is this kind of accreting massive black holes in the center of galaxies. Okay, what they discovered is that basically there's the foreground galaxy act as a lens, and they see two images of a background quasar. And these two images, if you take the spectra, they look basically the same, and they change in the same way. So this seems cannot be in two individual objects. Must be object. We see two images of one object. That's basically the gravitational lens quasar. Okay, we see these two images of the this lensing effect. Okay, so that's the first discovery, and then people start to study gravitational lensing in more details. And I mentioned a few of these kind of milestones here. 1991, so two astronomers at Princeton University, Moore and Pandinsky, they proposed that gravitational lensing can be used to detect extrasolar planet. So I will mention this later. And in 1993, there are two experiments or two collaborations. They start to discover the first macro lensing events towards the large Magellanic Cloud. Okay, I will talk a little bit about macro lensing. Okay. Then, towards the end of last century, people start to detect weak lensing by galaxies, okay, and try to study the matter distribution in the universe through gravitational lensing. And then at the beginning of this century, these two collaborations start to they discover the first extrasolar planet, okay, with the macro lensing technique. So during the past 20 years or 2 decades, this macro lensing or galaxy lensing or CMB lensing, there are a lot of observations and theories, and enable us to learn a lot about the universe. Okay, so the gravitational lensing has become one of the powerful tools for us to probe the universe. So I will show a few examples. So before I move on, are there any questions? Yeah.
Not right now.
Okay, good. Okay, then I will move on. So I will start with the macro lensing. Okay. What is macro lensing? Okay, suppose we have a background star, and then that's us, observer, this telescope. And in between the source, the star, and us, there's another object. This object could be another star, a sun-like star, a dwarf star, or a neutron star, or a black hole. As long as it has mass, it can act as lens. Okay. So everything is moving. So there's relative motions of this object, this lens, and the source, and us. Okay. Let's see what will happen if there's relative motions. Okay. So if the central object moves just in between us and the source, it can have this gravitational lensing effect to form two images of the background source, this background star. Okay. But in our Milky Way, with typical parameters in our Milky Way, the separation of these two images is too small to be resolved. It's basically around a milli-arcsecond, a very, very tiny angle. Essentially, with the very powerful telescopes, we cannot really resolve these two images. Essentially, what we see is still one image of the background source, but the total brightness is changing because now you have superposition of the two images. You get the background source appear to be brighter. Okay, so the total brightness change due to this gravitational lensing effect. And so what we can see is basically over time, the brightness change. So we'll see a light curve. Okay, so this is how we discover macro lensing events. Okay. So basically, the macro lensing is basically a background star lensed by foreground object. And what we do usually, basically, we try to monitor the sky, monitor the large Magellanic Clouds, there are lots of stars, or monitor in the bulge of the Milky Way, a lot of stars. So we take pictures, every day, and then we try to find that the stars change their brightness. Okay, and this light curve has really unique shape. So basically, also that the light curve have the same shape in different wavelengths or different colors, color independent. So that's how we identify these macro lensing events. Okay. So if we can really detect these macro lensing events, we can learn about this lens. So if the lens could be some for example, compact dark matter or could be like neutron star, black hole, or stars. We can basically map out a lot of things, learn a lot of things in the Milky Way. But if the lens is a star with a planet, then we can also see the gravitational effect from the planet. It's the gravitational lensing effect. Okay, so for normal star, we have this light curve with the brightness change as a function of time. And then if there's a planet, the planet also has this gravitational lensing effect. So on top of this lensing effect caused by the star, the planet also show up. Okay, the lensing effect from planet also show up with like shorter time scales. For example, the typical time scale for the brightness change is about like a month. And for the planet, it could be like a few hours. So basically, that's how we detect planet through the macro lensing method. Okay, try to see the on top of this the light curve, there's a little bit of short time scale change in the brightness. Okay, so that's basically how we can learn about the extrasolar planet around lens star. Okay. So in terms of the extrasolar planet, so first extrasolar planet is discovered through the radial velocity method. So basically, the planet move around the stars, and star also move around the planet. There's a little bit like a velocity change of the star. We can use Kepler effect, Doppler effect to really learn about the planet. So that's called RV, radial velocity method. So you can see, okay, in this kind of space, the planet mass versus the orbital radius of the planet. So this kind of radial velocity enable us to discover planets very close to the star or very massive. So that's basically that the radial velocity can give us. And we can also detect the planet using the so-called transit method. So like the Venus can transit in front of the sun, and the planet can also transit in front of their stars. Okay, they can cause tiny change in the star's brightness. And we have this Kepler satellite, the telescope, space telescope, right? So has discovered about a few thousand planets through this transit method. And for really big planet, we can use the direct imaging to discover this big extrasolar planet. But you can see macro lensing fill in this kind of nice gap here, can discover Earth-like planet, with separation about a few astronomical units, and with like a mass about Earth or higher. Okay, so that's the kind of like a complementary method to detect planet, and also enable us to map out the distribution of planet in full range of the parameter space. Okay. And so I just want to mention a very exciting new result called like a free floating planet. Planet, think about like sun or some sun-like stars. A planet got kicked out of the system. So the planet will become a so-called free floating planet. It just move in the space. Okay, and the thing that typically with any other technique we cannot really see this planet, but the macro lensing enable us to see through the gravity of the planet. So here is a discovery of a free floating planet earlier this year. So what happened is basically they keep monitoring the center of the galaxy and monitoring the bulge, and they found that there's change and very short time scale change, indicating it's a planet. There's no other object around. And what's nice about that is basically we observe this macrolensing event from the Earth and also through the Gaia satellite. Basically, you can think that through different directions. So the macrolensing event, this brightness change will have some relative time offset. Okay, and this in fact is helpful, very helpful for us to constrain the parameters of this lens object. It turns out it's a Saturn mass free floating planet. Okay, with this discovery, you should think that in the Milky Way there are a lot of planets, not moving around their stars. They just free floating in the Milky Way. This is a really exciting discovery. Okay, so that's a macro lensing. I will briefly mention a few of these kind of applications. Now I'm move on to gravitational lensing by galaxies and clusters. Is it true we will have questions in at the very end, or is the time also for questions? Yes, I can hear you.
It's your call, but does anybody have any questions thus far? I think we're good.
Okay,
Yeah,
great.
we'll wait till the end.
Okay, good. Then I will move on. So I will talk about strong gravitational lensing by galaxy clusters or galaxies. Okay, galaxy clusters. This galaxy or galaxy clusters act as a lens. Okay, can basically have gravitational lensing effect of this background object. This background object could be a quasar or a galaxy. Okay, so basically we'll see change in the shape of the multiple images. Okay, just give you some examples here. And so this one is basically image of distant galaxies, distorted by the gravity of foreground galaxy. The foreground galaxy show that appear to be this reddish object. That's the foreground galaxy. The background, the distant galaxy, is this kind of distorted image. This bluish image can almost a perfect Einstein ring. Okay. So we can also see others here. You can see, okay, this kind of Einstein ring-like features, but you can see individual images, like 4 images here. You mentioned the Einstein cross, this something like that. So it has individual images of background quasars. Okay. So then that's another cool thing. Okay, here galaxy clusters, have like 2 very bright galaxies, next to each other, act as lens, and then the background galaxy you can see shows that this arc-like feature, and this form like a smiley face, right? Cosmic smiley face, very interesting. So what we can do with this gravitational lensing, you can see, okay, there are a few things we can learn. We can study first the distant galaxies, okay, distant objects, okay, distant quasars. The gravitational lensing can magnify, the background source, basically enable us to learn more details about the background source. Even the background source is really far away. So in that sense, the gravitational lensing act as a really big telescope. Okay, help us to learn about the background galaxies or background quasars or objects. We can also learn about the foreground, this lens, this galaxy, for example, because the gravity is provided by the foreground galaxies. Then we can map out the matter distribution around this foreground galaxy. The matter provides the gravity. So basically, we can learn about, for example, the dark matter distribution in these foreground galaxies. Okay. And later, we'll also mention that if we observe these things at different redshifts, at different distance, we can also learn about the evolution of the universe. So you can see, okay, it's kind of like gravitational lensing is really powerful for us to learn a lot of things. We can not only learn about the distant galaxies, distant objects, but also the lens itself, the foreground galaxies. Okay, so another thing we can learn is that I mentioned, okay, these different images, when they reach us, they experience different lengths of the path. Okay, their travel distance is different because they get deflected differently. So it turns out if there's some change in the object, like quasar, for example, the accretion rate around the black hole changes, then the brightness of the quasar will change. But these different images, the change will arrive to us at different time, okay? Because they will follow different paths. So here example, here the you can think of that brightness as function of time. And in one of the images, for example, the red, the bright it's become brighter and then become fainter again. And in the another image, basically they're doing the same thing, brighter and fainter again, but with some delay in time, delay by, for example, probably just a month or a few weeks. So this delay enables us to map out the size of the universe, and which also enable us to measure the expansion history of the universe, measure the so-called Hubble constant, okay? How fast the universe expands. Okay? This is one of the interesting methods for us to, to infer or to measure the expansion rate of the universe. Okay? This is one application, one very interesting application of strong gravitational lensing. Usually when we mention strong means there's multiple images. Okay? So there's strong gravitational lensing, there's definitely weak gravitational lensing. Okay? What is weak gravitational lensing? Okay, so let's talk about the weak gravitational lensing. Okay. So the weak gravitational lensing is basically, you may not form multiple images, but you can still measure the gravitational lensing effect, because gravitational lensing can change the shape of the background source. So here, just to give you some idea, let's say, okay, I have a lot of background galaxies, circular. They appear to be circular. Let's say, okay, let's start with circular galaxies. If I have a lens, galaxy cluster or galaxy between us and this background, galaxies. So when we observe the background galaxies, their image got distorted because of gravitational lensing effect. You can see, okay, if there's a lens here, you can see all these kind of circular source, their image appear to be stretched and become stretched tangentially. Okay, you can see, okay, there's always get stretched. So we can measure this, the degree of stretching, and then figure out the matter distribution around the lens galaxies. Okay, but in reality, we don't have a perfect circular galaxies. Okay, galaxy has their own shape. Okay? Some all random orientation. We have like a disc-like galaxies. Different orientation give us different shape. But the lensing effect is very coherent. Okay? It's basically try to have this stretching tangential, stretching this galaxy image tangentially. So with a lot of galaxies, we can measure this kind of the degree of this stretching, and then map out the matter distribution in this kind of foreground lens around the galaxy clusters or galaxies, map out for example dark matter distribution in the universe. Okay, so this is called weak lensing. Basically, it's called the shape of the background galaxy to change, get this kind of shear. We call it shear or get stretched tangentially. We can measure this kind of this shear signal with this really large galaxy surface and map out dark matter distribution in the universe, for example. So here just just want to show you one of these exciting or intriguing result. So based on this kind of measurement, we can try to learn about the cosmic matter density, and also kind of get the structure, the amount of structure in the universe. Basically, we call it matter clumpiness. Sometimes we call it S8, or in fact more like an example called sigma8. Okay, we can measure this in using different observations. So from weak lensing, really large survey, weak lensing, we get some constraints, essentially, okay, get omega matter, the matter density, and its clumpiness. But we can also observe the cosmic macro background and also get the same quantity. Seems there's some disagreement. We call this S8 tension. Okay, it's not an exact tension yet. There's some tension, and currently, our task is try to understand what caused this tension. Is that called our measurement? Is there some systematic effect in our measurement we need to correct for? Or this just indicate our current the model of the universe need to be improved. There's some new physics, for example. So this is still open question. That's a lot of this large galaxy surveys trying to answer such kind of questions. Okay. So this is the weak gravitational lensing. So now let me just mention the some very cool applications caused by galaxy clusters. So if I have galaxy cluster, you can think of galaxy clusters are a huge amount of like a dark matter halo around this galaxy, around 1,000 galaxies. Okay, and this can basically give us a lot of this phenomena related to gravitational lensing. Okay, so this can give us magnification of the background source and also distort the shape. Okay, so we can use these massive galaxy clusters as a magnifying glass or giant like a telescope to study really distant galaxies. I think many of you may be familiar with this image, right? This picture. So this is the first release from James Webb's observation. So this is called James Webb's deep field, first deep field. It's a really long exposure, like about half a day exposure, and we can see really faint object, really distant object. Okay? So in this image, you can see some galaxies appear to be whitish. So these galaxies are kind of like galaxy in a galaxy cluster or closer to us. Okay, it's basically about like the light from this galaxy cluster traveled about 4.6 billion years to reach us. Okay? But you can also see some of these kind of red objects, these red galaxies. They are much more distant galaxies. The light may have traveled like 13 billion years to really reach us. Okay? So you can see, okay, this simple deep field image is basically our time machine, okay, to study the universe, to study the evolution of the universe. We look more closely, you can see there are a lot of interesting features. You can identify these arc-like features. This basically is gravitational lensing, caused by gravitational lensing. So this background, this reddish galaxies got gravitational lens, but the foreground, galaxy cluster. Okay? And we see this kind of like arc-like features because this background galaxy got stretched. Okay, their image got stretched. Okay, the one with the lensing effect. But there are other things we may not recognize. For example, there's some reddish, very tiny thing. In fact, this is a really distant object. Okay, let's zoom in. So this guy, okay, it's really distant object. And with GWST, we basically can take a spectra of this really distant galaxy. This galaxy, basically the light start to emit light when the universe is only 600 million years old. Okay? We take the spectra and we can identify the spectral lines that tell us this kind of like a chemical element. Okay, we can identify oxygen lines, hydrogen, neon, all these things, and we can learn about the chemical abundance of different elements in this really distant object. Distant because of finite light speed. So the distant object means like we're seeing the universe in the very early on. Okay, so that basically tell us about the formation of the galaxies very early on in the universe when the universe is only like 600 million years old, and we can tell what kind of element got formed there. This can give us a lot of information about the formation and evolution of stars and formation and evolution of galaxies. Okay, and this guy, in fact, we can identify the galaxies, but the James Webb Telescope can also discovered a very interesting type object called a little red dot. Okay? This appears to be really compact and shows really interesting features in their spectra. And we don't understand what's going on. And the current theory, one of the theories basically this could be just a very massive black hole that's accreting gas. And there's no host galaxies, no stars around it, just a black hole, very massive black hole accreting gas. So this little red dot, this is very recent, work paper. Okay, so So this little red dots, you can see there are 3 images. It's lensed by a foreground galaxy cluster. Okay? And the magnification, factor is about 6. Okay? So basically, this really help us to learn this object. Okay? And we can use GWST to really observe one of the images of this object. And it's very interesting, okay, from observe this so-called H-alpha emission. We see this, the gas, what shows up here is basically gas is moving around the central object. The central object is supposed to be a black hole. Okay? And you can see, okay, here in one side, the gas is moving, I think maybe, this is maybe moving away from us. In one side, the gas moves towards us. That means the gas is moving around the central object. So basically, we can get the kind of so-called like a rotation curve, from this object. You can see this really because of the landing magnification effect, we are able to do this. You can see, we really see details of this object. You can see the scale here is parsec. Okay? It's kind of like 100 parsec, very small scales. Basically seeing the very central part of the gas, okay, moving around the black hole, supposed to be the black hole. Okay, and use this, how this kind of like the motion of the gas, just like from the motion of the planet, you can measure the mass of the sun. Here, from the motion of the gas, you can measure the mass of black hole. It turns out to be like 50 million solar mass, so already very massive. And then this happened when the universe was only like 750 million years old. Okay, very early on, already have this kind of like a very massive black hole. And how you see, and with this massive black hole, there's no stars and no host galaxies. The question is, how do this black hole form? Okay, there's a theory saying that black hole may form before star or galaxy formation. There may be direct collapse of gas can form this very massive black hole. Maybe there's some like new physics. We may have some primordial black holes, things like that. Okay, so this is a really hot topic. It's maybe one of the most important discoveries by James Webb Space Telescope. This kind of little red dots. Okay, so still the nature of the little red dots still appear to be not well understood, but we think it's kind of like there's basically we are seeing like a black hole and with accretion of hot gas, and sometimes we call this black hole stars. Yeah, that's I think you'll continue to study such object. It's really like exciting and interesting discovery. Yeah. Okay, so with galaxy clusters, I also want to mention, I think many of you already know this kind of so-called bullet cluster, enable us to learn about the nature of dark matter. So what you see in this plot, in fact, through different observations. So this the whitish, these are the galaxies from optical surveys. So we take images of the space, this galaxy cluster. Okay, and in red, that's based through X-ray observation. This shows the gas distribution in the galaxy cluster. And then in blue, these are like a dark matter distribution, through the landing measurement. So we basically measure a lot of the distortions of galaxies, the background of the galaxies, and try to map out the dark matter distribution in this galaxy cluster. And you can see, okay, the galaxies seem to follow the dark matter. The white galaxies and form this kind of like a bluish dark matter, but the gas is not. Okay, and you also see there's some interesting feature here. So what happened here is that so we have the two galaxy clusters. They collide and they pass through each other. Okay, so just here, just simulation. So two galaxy clusters pass through each other, but the gas, they cannot pass through each other freely. You induce shocks in the gas. And the gas has this friction. Okay, but the dark matter and the galaxies basically can pass pass through each other freely. So this kind of like a difference in the distribution of the gas and dark matter enable us to learn about, for example, how the dark matter interact with each other. We call it weakly interacting dark matter, okay? So it's really hard for dark matter to basically to have friction, okay? And this is one of the famous, result related to the nature of the dark matter. In fact, this observation rule out a lot of other assumptions about dark matter or this kind of a theory about dark matter. Okay, so this is kind of like you can see gravitational lensing enable us to learn a lot about the dark matter, okay, and a lot things in the universe. Okay, so finally I will end with this another lensing effect called the CMB lensing. Okay? The CMB is a cosmic microwave background. Essentially, that's the afterglow of the Big Bang. We have this radiation. You can think the cosmic microwave background is composed of the oldest or the farthest light. Can be thought as from a surface very far away from us. Okay? So you can see this surface basically emit light around 13.7 billion years ago. Okay? And in the cosmic microwave background, so we can measure the temperature. Temperature is about 2.7 Kelvin. So very, very low temperature, around the absolute zero temperature. Okay, so 2.7 Kelvin. And but if we look at the different directions, the temperature appear to be slightly different. Okay, about millikelvin or microkelvin difference. Okay? So some places we see higher temperature, some places lower temperature. Very tiny, okay, about 1 part in 10 to the 5 fluctuation. This encodes very, very important information about the universe. This basic fluctuation will grow later, with time because of gravity. Okay, this you can think this is kind of baby picture of the universe, shows us these tiny inhomogeneities that in the end will grow to form galaxies and the galaxy clusters and form the structures of in the universe. Okay? And these CMB photons, on their way to reach us, they will pass through all this kind of dark matter between us and the surface of the CMB. Okay? So basically, this dark matter distribution will act as lens. So in other way, this background, the CMB photons will be gravitationally lensed, but matter in between us and the CMB, the emitting surface. Okay. So this kind of gravitational effect will basically have some small distortion in the fluctuation, this kind of temperature fluctuation, and also cause some polarization pattern in the CMB photons. Okay. Here that shows some distortion in the temperature fluctuation. You can see okay, there's tiny distortions with or without this kind of lensing effect. So with observed data, in fact, we can infer this kind of lensing effect and try to map out the distribution of the matter. Okay, so here is the result from the Planck satellite. So what you see here is basically along each direction, what's the projected matter density along each direction. Okay, between us and the so-called laser scattering surface, this surface of emission. Okay, from this we can also learn about how the matter distribution evolve with time, and to learn to constrain cosmological parameters. Okay, this is called CMB lensing. Okay, I think this is my last slide. I just want to stop here for questions. Thank you.
Do you have is mic up? Okay. What do we say? What exactly do you mean by matter clumsiness?
Oh, okay. So at the very beginning in the universe, you can see, okay, for example, here, in fact, this temperature fluctuation reflect, how the matter, fluctuate. So in fact, the matter in the very early on universe is very, very like smooth. Okay, can see, okay, the one region maybe is slightly like, overdense, the other region is slightly overdense, underdense, but the fluctuation, relative fluctuation is only like the 1 part in 10 to the 5. Okay, 1 part in 100,000. But these kind of like tiny fluctuations will grow with time because of the gravitational effect. Okay, the overdense regions become more overdense. The underdense regions become more underdense. So later, these kind of tiny fluctuations will grow and then form the structure we see today. For example, we see galaxies. We see like a galaxy clusters. These are all formed because of the tiny fluctuation very early on. But how this tiny fluctuation grow with time, that depends on our understanding of the gravitational theory. It depends on the expansion history of the universe. The clumpiness just try to describe this inhomogeneity of the universe. Okay. Does this answer your question?
Enough.
Okay, thank you. Yeah, basically describe like the amount of structures in the universe. Okay, it's not smooth. The universe is not really uniform, but there's structures in the universe. Basically, describe the amplitude of this kind of like density fluctuations in the matter distribution.
Okay. Thank you, Dr. Zheng. This is a really, really cool topic. I'm curious. I'll ask two questions, and they both relate one to another or to each other. Is the universe considered spherical? And if not, if it's more clumpy and say some egg shape or whatever it may be, as kind of represented in this slide you have here, what is the diameter or what is the long axis of the greatest part of the universe? What do they think it is? What do you think it is right now?
Okay, so just a clarification. So here, what you see here, if you think, for example, if you want to make like a map of the Earth, right? So one way to make the map of the Earth is basically, get this kind of more like an elliptical shape, right? You see all these continents and everything, right? So this is basically how we make the map of the universe here. So the universe, in fact, we think, along each direction, that's basically spherical. But when we make a map, we basically make a map like this. So the nice thing about this map is basically, so at a different part, the equal area here corresponds to equal area in the sky. So that's why we want to make this kind of map. So this map alone does not tell us the shape of the universe. Essentially here, we're still seeing a spherical shape because along different directions, we see basically essentially statistically speaking, the same thing. Okay. So in our observable universe, to answer your question, the shape of the universe, in our observable universe, okay, you should think like, the light travels along different directions in the same time, okay? So basically it's spherical, okay? But outside of this kind of observable universe, the universe may have different shapes, even like, have different dimension. But this, we have some like, theoretical speculations, but for now, we don't have an observational answer for this question, okay? So, and in terms of usually when we talk about shape, if you read some papers or some articles that may talk about the shape of the universe. There, the shape have different meanings. We usually say, okay, talk about the curvature of the universe. Whether the universe is more like, the Euclidean, so-called Euclidean, kind of flat space, okay, like, along each direction, there's no curvature, or it has like positively curved universe or negative curved universe, okay? Given our current observation, the universe appear to be really like spatially flat, just like the space we think of, like Euclidean space. Like if you think a 2D example, it's more like a plane, okay, along each direction. Not like a curved like the surface of the Earth, not like that. It's really like a Euclidean space, like a flat plane. okay, and in 3D space. Okay. I don't know whether this answers your question. First question.
Yeah, thank you. It's close to. I guess what I'm curious about then is what then would be the far side of the universe from Earth if we're looking at like estimated 13.7 billion years ago? What I always have trouble with is, I know the universe is immense, clearly, many billions of light years or whatever across, I presume. But if we're here on Earth and look one direction and we see a redshifted galaxy that's billions of light years away, and we turn around and look in the exact opposite direction and see a galaxy that's redshifted and is billions of light years away, then can I simply add billions one direction and billions the other direction? That would presume I'm at the center of the universe, which maybe we're really not. So what's the far side of the universe? How big is it? Is all I'm trying to reconcile. Thank you.
Yeah. So okay. Thank you for the question. Really a nice question. So when we talk about the universe, we should differentiate it like the observable universe. So our observable universe essentially that's governed by the physics laws, like the speed of light is finite. So that's basically the farthest object or potential object we can see is the how far the light can travel over the edge of the universe. Okay, but the real universe can be much larger than our observable universe. Okay, that's okay. But because of this, we are limited by the finite speed of the light, so we can only see part of the big universe. Okay, so the observable universe, as you said, okay, basically essentially is determined the distance you can see, the farther distance you can see, is essentially determined by how far the light can travel over the edge of the universe, basically over about 14 billion years. Okay, but when we talk distance, we should be careful. The universe also expands. It expands over time. In fact, the distance is larger than 14 billion light years, larger than that. Okay, the observable universe. That's I think what we can see. We can talk about the observable universe and talk about there's the real universe is much larger than the observable universe. And we are not at the in that sense we are not at the center of the universe, because if we change to another observer, for example, observing another galaxy, he will see the same thing. Okay, so basically again the distance, the farther distance he can see is basically determined by the how far the light can travel over the edge of the universe.
Zheng? Hello?
Yeah.
Can you hear me? My question concerns gravitational lensing again. If the large mass object is a black hole and it's between us and some object on the other side, in that slide there, which if the instead of a foreground galaxy it's a black hole, what do we actually see in the background?
Okay, that's really interesting. The thing that typical for if really for us the black hole. Okay, so that's okay. So if the black hole is a stellar mass black hole in the Milky Way, right? So we will have this kind of similar to this macro lensing event. So for example, if this is black hole, we'll get a similar effect. And depending on the black hole mass, so this time scale could be longer than typical stars. The black hole mass can be for example, 10 solar mass or 20 solar mass. Then the time scale will be proportional to the square root of the mass of the black hole. So time scale will be longer. So this is one way for us to discover a free floating black hole in the Milky Way. Okay. So far, all the black holes discovered, through this kind of the black hole in the binary star system. But we have one example that the free floating black hole in the Milky Way gets discovered by the macro lensing effect. Okay, it's basically black hole. The effect of black hole is not different from a star, from a planet. But there's interesting if we are very close to the black hole and the black hole is accreting, there's an accretion disk, there'll be a really interesting picture you see. And if you I believe you have watched the movie Interstellar, right? There, if you see the image of the black hole, that's basically caused by this, the emission, the source is basically the accretion disk around the black hole. And the light from there get bent, get deflected, really strongly deflected. We'll see very interesting features of this image of the accretion disk. Okay, look at the movie of the Interstellar, basically shows the effect.
Okay, great. Thank you.
Oh, is there somebody online that wants to ask a question? I thought I heard somebody online.
Was that me?
I don't know. Was it?
Oh, I can't figure out whether you can hear me or not because I'm not that
We
familiar
can
with
hear
this
you.
thing. Oh, okay. Hey, Zheng, this is Brad Jensen up in Utah.
Okay.
I was just over at your school today.
Okay.
But back to that question of how wide the universe really is. I've read this somewhere or learned this somewhere that when you're figuring out how many light years it really is from one end of the universe to the other, you take the 13.7 billion years that light has traveled. So that's one width, but you got to add to that how much space itself has expanded. Is that correct? And
That's correct.
when you add those two together, don't you get something like, my memory's not perfect on this, but something like 90 billion light years?
Yeah, something like that. I totally agree with you. That's correct. That's I said. Okay, so there's a little bit we need to be careful how we define the distance. Yeah.
Yeah, you really
Exactly.
have to. It's hard to get your mind around that, whoever was asking the question, but you
Yeah.
got to realize space itself is expanding, and the
Yeah.
speed of light through space is only the speed of light through space at its momentary
Right.
density. But then as space is expanding, that light is getting stretched in a way that is not faster than the speed of light,
Right.
but is the combined effect of space expanding and light traveling through it.
That's correct. And in fact, the expansion of the space itself could be faster than the speed of light. Okay.
Right.
Okay. Yeah. That's
Right. So then
very interesting
add the
effect.
two together, you're really looking at a speed that's it could well be faster than the speed of light, which sounds very counterintuitive. But at any one instant of
Yeah.
space's expansion, light can only travel at what it travels at, 300 meters per second.
Yeah, so that's basically in cosmology, we call this kind of distance, we call it co-moving distance, okay, which account for the expansion of the universe. So we can calculate that easily. Yeah.
Okay, hope that was helpful.
Yeah. Thank you.
Yeah, I have a question.
Yeah.
This is Theodore Smith. I'm out in Azle, and you were talking about the universe being flat. It's being Euclidean, so it's flat.
Yeah.
And that would be flat in any direction that you would care to look. Is that correct?
That's correct. So you can think it's as a 2D example, you think a plane, basically expanding plane, okay, along all the directions. And here we just it's become like 3-dimensional Euclidean space. It's just expanding Euclidean space.
But if you're talking about a plane which is floating in a 3D universe, you could orient that plane in any direction, and the spatial geometry would be flat. Is that correct?
Yeah, you can think instead of like a plane, have like a 3D like a coordinate system, a grid, right? This kind of follows the Euclidean expanding with time.
Okay. All right. Thank you.
Zheng, you're saying it's flat on average. The whole overall Euclidean space, it's overall looks like a very Euclidean space because it's not too curved in its entirety. But near a black hole, it's curved, right?
Totally agree with you. When we talk about cosmology, we talk about on really large scales, basically on the average on really large scales. We live in Euclidean space.
Okay, thanks.
Can you hear me?
Yes.
Okay, 2 quick questions. When you see multiple images of an object like your red dot, do you show the same object because they have the same spectra?
Yeah, typically, like we can tell, like from the spectra, and also sometimes, as I mentioned, like if you observe long enough, there's some like an intrinsic brightness change of the object. We'll see this image will follow the same change, but there's relative time, like no delays.
And the other, this kind of relates to your last question. If you go back to the beginning of the universe and all the mass is concentrated in a very small volume, you're in a very, very, very deep gravitational well. And this would cause time dilation and all sorts of other effects, would it not?
Well, that intuitively that may be the case, but in fact that's not really the case. So even like the density become really high, right? But if we start with, for example, a Euclidean space, if densities become really high, so there's this we still have the Euclidean space. The curvature of the universe will not change with time. So maybe it's counterintuitive, but like at the very beginning, you think that density is really high, but because everywhere is uniform, you can think in a way like the kind of like gravity cancels out. Okay, there's no real like a deep gravitational field. So it's still like a flat universe. If we start with a flat universe today, if we go back in time, we will still end up with a flat universe.
Yes, but I was thinking at the beginning,
Yeah, the beginning, yes.
and
So
would you not have time dilation at that point too?
oh, time dilation is a different time dilation. Okay, so that's related to the definition of the time. So the time is basically is kind of if you have an observer, uh, who goes with the flow of the universe, expansion of the universe, and basically the time he measures through the clock he carries. And that will be the same time as we measure today. Okay, it will be the same because that's based on Einstein's general relativity. There's the equivalence principle. It's basically saying that a freely floating like observer, there's no gravitational effect. Okay, but the time dilation you talked about is related to the expansion of the universe. Let's say, okay, if I have like something happened like in the distant galaxy, like explosion. The explosion in the galaxy's frame is the 1 second. Okay, but when we observe it, we will observe in fact the explosion lasts for like maybe 2 seconds or 3 seconds, depending on how far away the galaxy is. And this is time dilation effect. It's essentially the same origin as the redshifting effect. Okay, the wavelength of light gets stretched. So that's related to the time dilation effect. But if you are talking about the time the clock becomes slower, this kind of effect, when we go back in time, that's not exactly the same effect. In that, that clock we carry it by observer goes with flow of the universe will not change. The rate will not change.
You're going to be a large scale cosmologist. You're going to be asked the big questions, aren't you?
Well,
Does anybody else have any questions? Okay, hey, Dr. Zheng, thank you for your time with us. It was a really fascinating topic, and thank you so much.
Yeah, nice to meet all of you. Thank you. Okay.
Take care. You're welcome to stay on the Zoom call if you'd like, or feel free to.
I will say bye. Okay.
Right. Thank you, Dr. Zheng.
Bye.
All right, good stuff. Next slide. All right. Quick 10-minute break. So when this says 3:29, we're going to start again. We got a bunch of stuff to raffle up here, so come buy a ticket. So we'll be back in 10 minutes. All right, grab your seat. We'll start with the raffle so we can move through the rest of the stuff we got going tonight. You got those in there? I'm ready to start. Yeah, they need to go in. Yeah. Oh. All right, first ticket. Wow. 155500. 155500. 15500. Oh, here we go. Come on up. Next ticket after him, 155510. I'm sorry. Yeah, 10. 000. Yep. Don't drop it in. Yeah, there we go. 155510. All right, Dave. Next ticket, 155536. 155536. Christian, come on up. Next ticket, 155519. 155519. All right. All right, let's spread the numbers out a little bit. Next one after that, 155466. 466. Michelle? All right. And next one, 155539. 539. All right. Yeah, 2 in a row. Next ticket. 155512. 512. Last three of 512. Charlie, all right. Next one, 155493. 493. Anybody got 493? We'll move on to the next one. 155509. 509. That's you. Sure? All right. Last three, 467. 467. Passing? All right, sorry. 486. 486. All right. Next one after that is 474. 474. I will. This may be you too, 478. 478 you as well? All right. Last three, 523. I'm sorry? $474. Yeah, no, there's the 478. All right. 523. 523. Anybody have five? Huh, Christian, you done? Oh, you can get another. Grab some more. More the merrier. All right, good for you. We're going to do three more. 531. 531. 531, anybody? $559. $559 already. And 525. That's okay. 525. No, no 525. 492. 492, anybody? All right, last call is 495. Same person, probably. 495. All right, that'll do it for tonight. Next slide. Most exciting part of the night. We'll give it over to Bill.
Okay. I have to turn the lights off, which means I don't have to turn the lights back on and kill y'all with your eyes. So this is everything that's going on for the next month before the next meeting, featuring Sean Paul's lovely picture of the pillars of creation on the front. Next slide. And of course, something that's so iconic can be something that can be photographed by us. Next slide. Bright comets this month. So we've got 10P, Temple 2. This is the one that's gradually getting brighter into the summer. We're probably near peak. Yes, we're actually near peak. It's going to be peak brightness on August the 3rd. And this is another dude that I follow on Astrobin. His name is Taras. Not even going to try and pronounce his last name, but he's been imaging comets as a part of the science for decades. So yeah, he's pretty cool. Next slide. Occultations and close approaches. So Saturday, August 15th, near dawn, Jupiter and Mercury are going to be 33 minutes apart from each other. It's going to be really low on the horizon, but pretty cool little conjunction there. And this is Mike Jones's image of the Jupiter-Saturn conjunction in December 2020. Next slide. So it didn't happen, but it's gonna. Just you wait. Next slide. Next slide. For those of you like two shadows on Jupiter, there's one on Sunday, August 9th. And it's happening in the early evening, so it'll be just getting dark. This is my only picture of a double shadow transit. Next slide. Okay, so asteroid 3, it's the third, that was getting in the way. It's the third asteroid that was discovered, Juno. It's the 10th largest asteroid at magnitude 9.1. It's going to be in opposition in the constellation of Aquila, which is about coming towards straight up in the sky as the night goes on. But yeah, so it's another asteroid that's going to be close to us. Next slide. Pluto. So I don't ever talk about Pluto. So Monday, July 27th is this year's opposition for Pluto. And if you've ever looked at, if you're familiar with the Sky Live, it's a website where you can actually see exactly where something is in the sky at the moment, and actually a pathway of where it's moving for, like, what incremental times or anything. So I've seen, to be able to look into the telescope and like right now it's in Capricornus, right? It was in Sagittarius when I was looking at it, and to be able to look at Sky Live and say, oh, okay, so that's where Pluto is, and be able to actually see that in the eyepiece is very cool. Also, that because Pluto is closer to us than it is at its furthest point, the difference, I've talked about the size, the apparent size change between when Jupiter is the furthest from us and when it's the closest to us. Well, the difference between Pluto at the furthest from us and the closest to us is 48 milliseconds. So jump on this one. Next slide. Okay, so there's the Delta Aquarids meteor shower. So this one is, it actually overlaps with the Perseids, which we'll talk about in a second. And the peak is actually on the night of Tuesday, July 28th. Goes through the night into the early morning. Didn't see what the moon was, but I don't think moon's, yeah, it's going to be a full moon. So this is kind of a bust, but it's got about 15 to 20 per hour at best. And you might end up seeing some with the Perseids, which is extremely favorable this year. Next slide. Yeah, full moon straight up. So July's full moon is on Wednesday, July 29th. This is another great Robert Cargill moon picture. Next slide. Mercury in the morning. So we've got Mercury at greatest western elongation. That's on Sunday, August 2nd. It's going to be the highest altitude, about 17 degrees above the horizon at sunrise. And Yeah, it'll be the highest on August 4th. Next slide. Okay, so do y'all remember? Hey, can you go back? Can you go back to the next back slide? So do y'all remember asteroid 1526? Come on. I'm just kidding. So so that asteroid that I was talking about last month, that was like close, like a near Earth asteroid. Somebody imaged it. There's a few people that imaged it. This was actually the best one that I'd found. Go ahead and play it. Play it. Yeah, there you go. So that's not in real time. Of course, that's time lapse, but it's a to see the motion of something in the sky, especially in the eyepiece. It's pretty cool. So next slide. Other next slide. There you go. Asteroid 173561 2000 blah 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 is going to be the closest to us on where is it? August 8th. It's going to be magnitude 13.1. Moving pretty good through the sky there. It's going to be at the closest. Brightest on August 8th, closest on August 9th at 13 lunar diameters. So, one of those, and a pretty good size too, about 565 to 1265 meters in diameter. That, it's one of those that you'd be able to see in the eyepiece actually moving. So it's a cool thing to look at. Next slide. And then there's new moon. Hey, Sean, another picture of yours. So we've got the new moon on Wednesday, August 12th, which coincides with so many wonderful things. This is Sean Paul's image of the total solar eclipse in 2024. Next slide. So if you happen to be somewhere between Greenland to Spain, on August 12th, you get to see the newest moon. We got a total solar eclipse going on there. It's actually a pretty good one from length of time, even though the one next year is going to be longer, and probably I think it's the longest one that any of us would see in our lives is next year. But get timing specs on timeanddate.com, and exploratorium.edu has actually got a live stream that's set up to be able to watch the eclipse. I think NASA probably does a little broadcast with that too, but you can look for those things on. It's like, see, down, going, and then it's like, so what you're seeing there is you're seeing that it's almost a sunset eclipse, which is a pretty cool thing. Next slide. Okay, and the Perseids. The peak of the Perseids is happening on the same night. So we got new moon at the peak of the Perseids, one of the best meteor showers of the year. Not just because there's a lot of them, because what is it? Like anywhere between, I've seen 60, I've seen up to 120 in the ZHR number. But it's also because it's not freezing cold like with the one in January. So it's all night long. Perseus starts coming up in the sky, and you get meteors all over the whole sky. So I'm sure that you've seen it before. This one's definitely a good year to see it. There's been way too many years lately where the moon's just been getting in the way. So this ought to be a winner, and hopefully we got clear skies. Next slide. Venus is highest and brightest on Saturday, August 15th, 34 degrees above the horizon at its usual magnitude of -4.3. John McCrae actually has this image of Venus in the Pleiades and the Hyades. There. Good shot. Next slide. All right, so I am featuring a southern constellation this month, and it is Musca, the Fly. So there are no named stars in it. It's actually a very small constellation. as far as size is concerned, out of the 88 constellations, it's 77th largest constellation in the sky. And speak a little bit about where we get this constellation from. If you go to the next slide. So, you know, I love the etymology of these things because it goes through so much before it actually landed on the list of constellations that we see today. So it was one of the 12 constellations conceived by Dutch navigators Keizer and de Houtman in the late 16th century. Okay, and so they called it the fly, the Dutch word for the fly. And then Plancius put it on his 1598 globe, but he didn't name it. So he put a fly. He put the thing on the globe. He put the constellation on the globe, but he didn't give it a name. And then Blau called it Musca, which is Latin for fly, on his 1602 globe. So this is the first time referenced as Musca. And then Johann Bayer included it with his Eurometria in 1603 and called it Apus, which is Latin for the bee. So it went from a fly to a bee. And then Plancius decided 12 years later that he was going to go ahead and name his constellation now, and he called it Muia, which is Greek for the fly. And so we're kind of having a hard time picking a language here. Apis and Musca were both used for 200 years after that point. And the problem is that Apis, which is the bird of paradise constellation, was confusing. So it was like, well, we don't want an Apis and an Apis. So they just stuck with Musca. And then Nicholas Lassalle, he named it Musca australis in 1756 because there was a northern fly at the time. So I'm not even halfway through the constellations. I've been doing this for like 2 or 3 years now. There's 88 of them, so 88 months, do the math. The thing is, at the end of those 88 months, I was thinking about starting to like talk about obsolete constellations. That ought to be a real kick. So northern fly, mark your calendar. Yeah, there was a northern fly at the time, so Musca australis, and then Musca australis, Musca borealis stopped being a thing, so they just dropped it and went to Musca. So now you know everything about the etymology of Musca. You're welcome. Next slide. So, GU Muscae. This is a nova. This is a binary system, and one of the stars is actually suspected to be a very high density star, like a neutron star or even a black hole. It's got an immense amount of X-ray energy that comes from it. The energy of X-ray and optical with a regular nova versus this one is just 1/10 millionths. So this actual the X-ray energy that's coming from this binary system is actually 10 million times greater of a energy ratio between optical and X-ray than with a regular nova. So there's definitely something really thick and dense there. Next slide. And wait for it. Next slide. There it is. That's when it goes nova. Next slide. The engraved Hourglass Nebula, not to be confused with the Hourglass Nebula in the northern sky somewhere. It's planetary nebula. Like we all know, planetary nebulas are the expulsion of the shell of a dying star. And a really beautiful shape here. Next slide. Is the shape of this is very likely due to the effect of an orbiting companion and its gravitational effect on the gas that's being expelled from this thing. So next slide. NGC 5189. So this is also known as the spiral planetary nebula because it looks like a barred spiral galaxy. Its shape is also explained with the influence of a companion star. Next slide. So just a really stunning object there. Next slide. And then there's the dark doodad, because I don't know. Like they just ran out of, I'm tired. The doodad. It's dark doodad. So it's also known as Sandquist 149, which is kind of like the southern hemisphere's equivalent to the Bernard dark nebula catalog. It is probably, it's part of the Musca molecular cloud, and it's pretty good size there. It's about 3 degrees in length, and the measurement of the magnetic fields of this lung doodad suggests that what we're looking at is we're looking at an edge-on view of what is really a sheet. So next slide here, and you can imagine that. There's the doodad. But yeah, what they think is that actually we're looking at the edge-on of a sheet of matter there. So it's pretty cool. Next slide. So for a full listing of all 9 of the things that are in Musca, I told you it was a small constellation. You can look these things up here, and more about the X-ray Nova Muscae 1991, which is that the binary with the companion star that's probably either a neutron star or a black hole. This is a really cool article right here to read. Next slide. And this shot is Christopher Ashford's Cat's Eye Nebula. What you see in an eyepiece is going to be the little middle bit there. What you see outside here is all the hydrogen and oxygen that's ionized stuff that you're only going to see photographically, but a very beautiful shot there. And keep looking up.
All right, next slide. All right, next slide. So we've gone through the committees and liaisons. Next slide. Just a quick overview of what we got. Of course, Matt's our registered agent. Membership committee, we got Maru, Sean, John. We got our observing area committee, architecture committee. They're actually going to get a brief here in a little bit. Noble observations, Noble observatory operations committee, outreach, 1687. I'm going to pick that up from Robert. Next slide. Got more. Tiny Hills, John and company there, Paula Pinto, Michelle and Tom. Copper Breaks, Gary and Tom. Whiskey Ranch, Chris and Christian are helping out on that one. Tom's going to take out Rising Star Library Liaison. Thompson Observatory is Robert Circus. 3RR, Michelle's going to give a little brief on that in just a little while. APSIG, Robert and Stephen Kennedy. Of course, Chris does our YouTube stuff, newsletter. We got George. Astro League, me and Tom Schneider are taking care of that. We're going to give some classes on Astro League programs. Zazzle, where I got this shirt from Zazzle, plus other merchandise. That's John Paul. Big Frog, that's the shirt that he has on right now and Christian has. Christian and Michael Tier are taking care of that. Fundraising, we have Robert Circus and Bill Hall. Here's where we need help. Next slide. All right, Dinosaur Valley. Patrick does that. But if Patrick can't go out there, I need somebody as a backup for Tiny Hills. I'm sorry, for Dinosaur Valley. If you're interested, or if you go out there quite often, and just to be his backup, we could use some help on that. Telescope observing and training. We're trying to put together some classes. I'm going to talk about one of them, but we're looking at giving some classes like, okay, we get new people here. Let's show them what we got, show things. Or we go out to Rising Star. Let's show star hopping. I'll do some star hopping demonstrations. Tom and Kurt were talking about putting together a little training class on the Astro League, binocular observing program, that'd be a good one. But if you got something that you got to share, that you could help people with, like, hey, how to use a DOB, because I don't know how to use a DOB, but I can teach people on SETs. You know, if you got some skills, we can use it just to give classes to new people and such. All right? So if you're interested, see me afterwards on this. Young astronomers, we've lost our venue on that, so we're looking for a new venue, and we'll figure that out once we get things figured out. George is our website coordinator, but if anybody else has website design skills, I can use some help on that. After we get it all set up, we just need somebody to go in and, hey, update, change this page, hey, the meeting room changed from there to here, things like that. So we use some help on that one. And then Facebook, Christian had been done that for years, but we need somebody else that can help out on the Facebook page, updating that, put some notices out and such. All right, next slide. So if you're interested in joining one of the committees, let me know. If we can all do a little bit, we can accomplish a lot. So everybody just join in a little bit. Next slide. I'm going to hand it over to Natalie Bruce, and she's going to give an update on the Architectural Review Committee report. Natalie.
Yes, great.
You got it.
I'm here. Okay, so if somebody will just run the slides for me, we will give you guys an update on what's going on with the Architectural Review Committee. So the Architectural Review Committee was created basically to look at the rising star observing area and create a long-range master plan. So the reason that we want to create a master plan is because there are ideas for a lot of projects out there, and creating a master plan will help us complete these projects in a logical sequence. It will help us ensure that we have room for future improvements. And also, it's going to create a framework for budgeting and fundraising, because we'll be able to look at, here are current projects that are coming up, here are future projects, how are we going to allocate resources to get all of these things done? So the master plan will basically be our roadmap for how we want to develop Rising Star in the future. And we'll be able to give the board basically a whole plan instead of kind of giving them isolated projects. So next slide. So what the committee has been busy doing so far in the couple of meetings that we've had is that the first thing we did was we looked at the member survey results, and that was the member survey that was administered earlier this year. And there were some pretty definitive results from that about what people would like to see out at Rising Star. And the top member priorities were an improved restroom of some kind. That was basically the top one, which would include some type of water, basically a water source to run the restroom instead of the compost toilet that's out there right now. A roll-off observatory for the club scopes, and conditioned space for the bunkhouse. So those are basically the top three things that we want to be sure we look at and see how we're going to address those and in what order. So we've also looked at the existing site conditions. We have the survey. We know what elements are out there currently, and then we can kind of assess how we might utilize the rest of the site with the space that's remaining. We are also in the process of gathering utility and infrastructure information so that we can make informed decisions about having infrastructure installed that will support future projects as well. And then finally, sorry, the screen got a little tiny up there. I can't see it. So we've identified the project priorities, and we are working on developing a preliminary site concept. So next slide. So what we have here is a preliminary concept. It is a working concept, just basically a place for us to go ahead and get started. And some of the things that have been discussed, and you heard Sai mention them at the beginning of the meeting. We want to ensure that there's parking for vehicles and parking for RVs. One of the things that we would be looking at, of course, is when it's dark out there, which is when a lot of the programs are going on. We don't want to have a lot of pedestrian and vehicular conflict because it's dark. So how do we, you know, put those elements in a way that makes logical sense to minimize that conflict? We want to be sure that we have room for emergency access. You know, if somebody should experience some type of medical situation, we want to be sure that responders can get in there and provide care to anybody who needs it. Developing a restroom is going to require a leach field, so we have to consider where that element would go on the site. Some of the other things are, there has been discussion about creating basically an education building where you guys could have sessions and then basically, you know, walk over and take those skills over to maybe, you know, the roll-off observatory or the pads and work on the things that you've just learned. Currently, the name for that is the Discovery Center. And you guys have heard it mentioned in the survey that you guys want to have a roll-off observing terrace where we can put the club scopes out there. There will be 6 piers. There's been discussion about creating additional roll-off pads and possibly some additional public or leased pads. But basically, you know, we're taking this, we have to figure out what size these elements need to be and how to put what things should go next to each other and what things should be spaced far apart and what order these things should be developed in. All right, next slide. So basically, the next steps for the committee are to continue gathering information and refine the planning concept, and then we will take those recommendations and present them to the board. So this master plan will identify what we want to accomplish over time, and the fundraising committee will then be tasked with working on how some of these individual projects can be funded. And those efforts are going to complement one another. And with that, I will turn it over to the next committee.
All right, next slide. Thanks, Natalie. Looks great.
Sure.
Financial report, Constantine.
So can y'all hear me okay? All right, so let's talk about the treasurer's report. As you can see, current report balance, $114,000. That's got to be the largest balance in the club's history. I don't know this for sure, but I'm guessing. This is due primarily to a $65,000 donation for observing terrace and other improvements at Rising Star. The other income is primarily from our membership renewals, and we'll talk about that a little bit later. The $65,000 translates down to the Rising Star Observing Area Development Fund, and you can see our current balance there is $67,000 total on that. And our outstanding loan on that is $978, which we anticipate paying off no later than October at this point. Now, let's talk about this $114,000. We've prepared this second slide here to talk about how that's allocated. During the first part of the year, we came to you and talked about establishing an operating cash reserve, and we've done that. And we developed a formula, and each January we'll go through that formula and come up with what that value is. For 2026, it's $21,600. Now, what we've done is we've taken part of that and are establishing CDs, 4-month CDs, $61.50 each. One has already been established. The second will be established the end of August. And we've done that staggered so that funds become available every 2 months, and we'll keep renewing those. In addition to that, there's a fluctuation amount, a reserve, that will stay in our checking account. Secondly, at the beginning of the year, we also identified the fact that we had about $20,000 available for us to invest in the livelihood of the club in different projects. Those dollars are still available, and what we're doing is putting those in a couple of CDs for now, also staggered, so they too become available every 2 months. The total was $20,000. That was reduced a little bit because we spent some of that money in purchasing the mower. And then the third category, we've received a total of 3 donations for the Rising Star observing projects. Any questions on that? Yes, sir. Sure, that's a good question, and I'll try to answer that best I can. As you know, there is an architectural committee currently underway, and they're working on that overall plan, and we'll also be looking at submittals for the various projects. The money was made available to the club. We received it and are holding it for that specific project. If that project doesn't happen, if the membership decides we don't want that observing terrace anymore, then we will return the funds, basically. But there are basically two amounts. One is for the observing terrace, and the other portion of that is for other improvements, other amenities at Rising Star, somewhat defined but somewhat vague. So we will take a look at the donation, and there was a definite description of how these funds are to be used, and when they coincide with our proposed improvements, then we'll use those funds. Otherwise, I think they'll have to be returned. Any other questions on that? Okay, let's talk about the last slide that I prepared here for everyone, and that is kind of a summary of where we are with regards to membership renewals. This year, we started in May with about 240 members, and we tried to renew 240 members. Only 179 renewed, which basically is 75% of the total, which is not real high, but it's very close to what we've done historically also. The interesting thing to me was that from 23, 24, 25, and so on, we experienced an increase in membership, an increase in the number of people that renewed, except for this year. It's the same as last year. Total income for this year's membership renewals is $9,760. If you haven't renewed, please do so. There will be an email that goes out here shortly that talks about the fact that if we don't receive any renewal from you, you will be removed from the system by the end of this month. And that's all I have. Thank you so much.
All right, executive board update. Just got a couple things. We got 4 things we're talking about tonight, so I won't go into them. But one thing we did do, we get a free Solar Observer's Handbook. It was sent to the club. If somebody wants to take this home and bring it back next month, it's got some really good stuff about solar observing. That was one thing that we got. Other things we're working on. We had a team that's going to look over our code of conduct and hold harmless agreements. We're going to update them accordingly. Things have changed over the last couple of years. We've got a team of 4 that are going to work on that. Sean Paul's in the process of giving us new business cards. We got a great design we picked the other day, and we're still working on finding an vendor and do that, but hopefully in the next 6 weeks we'll have some cards on that. And then the other thing we talked about was having a mowing party out at Rising Star. We got the same 3 people that keep mowing the place out there. But we got this great mower, and instead of 6 hours, it only takes an hour and a half to mow. I don't know how to use it. A lot of people don't. So we thought about having a little party out there and show you how to use the mower and use the various things out there, so we can have you get out there every couple of weeks and help us out. So we don't have the same 3 people mowing all the time. But we'll get more information on that. But that'd be helpful. And then I'm just reiterating the training team. If you got some skills, you want to help us with some training, or if you got some ideas on training, please get a hold of me. Next slide. No updates on that. Next slide. Other business, we're going to get into that. Next slide. Monthly reports. I don't have any announcements per se other than what I've already talked about, so we'll just give it out to Patrick. Come on up. Oh, well, I think we have something on the line. Let's beam the slides up. Why don't we, I know your slides are in there. So Chris, are you online to talk about this? Ms. Ashford?
Yes.
All right, you got it, Chris.
Okay, we got Bob has got the Noble Observatory Information Center up and running, and we've got 16 members have registered, and now he wants to open it up for anybody. He opened it up for the APSIG, so anybody that's been coming to the astrophotography special interest group, they will know about it. But I think he'd really like people who are not astrophotographers to register and try to use it, because sometimes things we take for granted are not entirely obvious. It helps Bob to tune his software and make it a bit more user friendly for people who are not used to astrophotography. So he's planning a next update will be middle of August. The last piece of it is to integrate the planning side, which is what he's already got up and running, integrate that planning with NINA. NINA is the application that runs on a little computer right by the mount, and that runs the imaging session. And that computer runs something called NINA, and Bob found that to be a lot more difficult than he thought it was going to be, so that's why it's a bit late. And Bob wants to officially launch the whole project as complete on October the 15th. So it's coming up, and we just need more people to log in and create an account and test it. Next slide. All right, now we had a nearby lightning strike, and that took out the transformer that provides power to us. So those of you that understand electricity will know that electricity on the power poles it comes at a high voltage, then it has a transformer which converts it to the power that we use in our homes today. Anyway, that transformer failed due to some sort of light. I don't think it was struck itself, but there was a strike nearby, and any lightning strike creates a massive wave of electromagnetic radiation, which is picked up by wiring and converted into electrical energy, which then basically caused the transformer to fail. So that then propagated into the propagated into the RSOA area, and the Noble Observatory in particular had some damaged electronics. Personally, I think we're lucky not to have damage to other components that were in the 40-foot container. It seems that the only damaged areas were in the Noble Observatory. So the peer-side computer, that's been fried. The network switch that drives the Ethernet out to the pads, that was fried too. And we also found that the earthing bond, usually, every house will have a spike in the ground, and usually it's near your power panel where your electricity comes in. Anyway, that connection was disconnected, damaged. We don't really know why. Bob thinks it's from a lawnmower strike. Could also be a squirrel or a rat. They like to sharpen their teeth on things like this. So anyway, we got some cable damage. We had surge protection, and those of you who are familiar with this, the power strips you buy from Walmart, they're typically 1400 joules of power of surge protection, and we had 3600 joules of surge protection in the Noble Observatory, but that wasn't enough. So it was we call it an act of God. I mean, it was an unprecedented event that fried some of our electronics. All right, so that's what happened. Next slide, please. So there's been a lot of email traffic back and forth. I've spent hours with Bob going through all the equipment. What is the replacement? Do we need to replace it with something different? We had a lot of help from Michael Tier. He's an electrician. I think there's a slide here which with all the names of the people who helped. So maybe I'll come to that in a minute. But here's a timeline. We're going to get it all fixed for July the 25th. So we know what needs to be replaced. And I've got a slide on the cost of all that in a minute. Yeah, the board really had to sort of step it up a gear because it was outside our normal meeting. So a lot of discussion on email, and the consensus was, okay, let's go ahead and buy this equipment. So next slide, please. So here's the list of equipment. On Zoom, I could barely read it, but I know what it says. The equipment grounding, well, that's fairly inexpensive. There's an HDMI cable that was damaged, $10. The peer-side computer, these Melee computers, they range in price. They're about $500, but somebody has generously donated one, so we don't have to buy a new one of those. Then there's the TP-Link switch. That's what drives all the Ethernet out to the pads. We've got to replace that. We're going to buy a second uninterruptible power supply, and that uninterruptible power supply, at one point it was in the Noble Observatory, but it was moved to the 40-foot container because it was considered that, well, the Noble Observatory is a secondary feature of RSOA. We should really be protecting the main network. So we moved it into the 40-foot container. It does come up. It does come with some surge protection, and so we're going to buy another one. Excuse me. We're going to buy another one for the Noble Observatory. Strictly speaking, that's nothing to do with the lightning strike, but it just seems like, yeah, we really should have that. And that was discussed at the board meeting, that we need one. And then a range extender. The range extender gives us two ways of accessing the web-controlled switch that's in the Noble Observatory. So it gives us a backup way of addressing that switch. The weather station, actually, that's been checked out and it's okay. So there's no damage to the weather station. So we can strike that from the list. And then there's a lot of discussion about, well, could we have a better surge protection mechanism? Because we had double what people normally use, and that wasn't enough. And yes, there are surge protectors you can install in the circuit breaker panel. And so we're going to buy two of those. And by the way, we have a top of the range panel. I mean, it's designed for long life, durability. It's really a very good panel. And so we can buy surge protectors for that panel, which are made by Square D. That's the manufacturer of our power panels. I'm going to buy two of those, and they work differently to the surge protectors you buy from Walmart. They operate in nanoseconds. When they see a high voltage or high current coming in, then they basically divert that current to ground, and everything's protected right there. Okay, let's see the next slide, please, Sai. Here we go. So there's me. So I mentioned it already that Michael Tier is an electrician, so he was involved. Peter designed the network, so he's been involved. Bob was the guy who drove out there to find out why the power had failed, why nothing was connected. Jim, he knew about all the components that we actually have installed, and he's the one that recommended the surge protector that we're going for. And then Kevin is very experienced, high voltage engineering consultant. So everything sort of bounced off Kevin. Hey, is this going to work? Yep. So that's the team, and that's the end of my presentation. Any questions? And if there is a question, I can't hear it.
Nope, nothing from this end, Chris.
All right. You want to go back to the cost side just for a sec? So the board did approve that 1,047 and a few cents. I can't remember what the cents were, and I can't read it on Zoom, but I think that, I think it's 1,047. So yeah, Constantine, we're going to be spending a little bit of that money. Sorry. But this is quite an unprecedented event. It makes you think about your own home. Maybe you should buy surge protectors and plug them in. They plug in just like a circuit breaker. They plug into your main power panel, and they divert current. And in this case, these surge protectors will divert 2 to 5 kiloamps. And we'll be well protected with those.
Anything else, Chris?
No.
All right, next slides. Michelle.
All right, and I'm sure everybody knows about it. Three Rivers, we've got our, okay, I'm in the right place now. We've got our Three Rivers Ranch field trip scheduled for September 4th, 5th, and 6th. It's Labor Day weekend. It is approximately 3 hours drive from DFW. I sent out an email with details a couple of days ago. I've heard from several people. Accommodations, the club actually rents 2 bunkhouses, one for the men, one for the women. We also have cabins available. Those go into a lottery because everybody wants cabins, and we'll draw at the August meeting for who gets into the cabins. We'll find somebody who's not registered for the cabins, so it will be a fair drawing. that was a good thing. We have RV sites available. Some are electric only, some are water and electric. If you want to be adventurous and camp, you can camp. Any of the RV sites, camping is like $10 a night, and of course the cabins are something that you yourself would pay for. And I listed the cost of all those items in the email. You can always check with me if you have any questions. Some people have learned that instead of camping, you might as well just stay in the bunkhouse because it's free and it's air conditioned. So that's always good. You can bring your own scopes. Then you've also we'll have volunteers there, and they can man some of the scopes that are at Three Rivers, so that we've got somebody who's an expert at that, like it's a 30-inch Dob, and you can just see some beautiful stuff. Yeah, there you go. And so it's just fun to go out there, whether you're with your own scope or going to observe and see what somebody else can see in those large scopes. It's really a fun weekend. And during the day, you can sit around and visit with other people. We've done that even when it's been raining. So we get a lot of good club membership time and get to learn about one another. Let's see. Oh, Saturday night meal. We do usually, you're responsible for your own food. You can pull off at a Walmart right off of 287 and load up on anything you want to load up on. But we've also got a Saturday evening meal that's catered. The cost for that is $20 per person. So if that's something you want to add, you can go ahead and just let me know and get me $20, and we'll get you in on that catered dinner. Questions? Yes. Did you get the email through Night Sky Network? We'll work that out after the meeting. We'll get together and make sure I've got that information to you. Okay. Any other questions? Yes.
Out at Three Rivers Ranch, the roof blew off the 30-inch or 30-foot building and 30-foot telescope. Anyway, they are in the process now of putting a roof on it. The frame is already there. Hopefully they'll get the rest of it done this month, hopefully. And we'll get the 30 put back in there and assembled and ready to go. I think you probably ought to have somebody to contact to find out if you're really wanting to look through the 30 to make sure it's going to be.
Okay, I'll check with Katie.
Yeah, talk to Katie, yeah.
Okay, thanks.
All right, the Astronomy Convention is in Cincinnati, August 12th through 15th. These are always kind of cool. I went to the one in Minnesota about 10 years ago. But it's always a thing to look at for the future. They go to different places throughout the United States. Next slide. All right, Chris, you going to talk about this while Patrick does, or while Christian does the stuff up here?
I'm going to talk about it. So, shall I start?
Yeah, go ahead.
Okay. So we really, really wanted to recognize the people that regularly come out to our outreach star parties. And so we were dreaming up ways in which we might do that. So next slide, please. So, so for club members who volunteer at star parties, and that includes the 1687 Foundation and the Whiskey Ranch star parties, we've developed a pin. And this is what it looks like. It's based on volunteer hours recorded in Night Sky Network. Now, and we set the threshold at 24 hours over the course of the calendar year, so January through December. And I'm aware that I've been to star parties where I know people, I saw people volunteering there, but I don't see their hours in Night Sky Network. So we're going to make some awards, but then I'm going to run through how to register your hours in Night Sky Network, because I really would like everybody to do that. And there's a benefit to the club as well. Night Sky Network hours recorded for outreach, they're reported to the Astronomical League, and then we get goodies from the Astronomical League. And so there is a benefit to the club, it's not just to you, for putting your volunteer hours in. So next slide, please. So these are the people, and Christian is there with the pins. And we'd like those people, if you're at the meeting, please come to the front and receive your volunteer pin.
I know a couple of you are here. Come on up front.
Yeah, and if you're not there, that's okay. We'll find you. And you will receive the pin one way or another.
Huge round of applause for everyone. And I appreciate each of your service one at a time. So first of all, thank you very much. 2026 edition. Michelle, thank you very much.
Thank you.
Bob, very much for all your hard work. And of course, Patrick. Thank you so much. Tell you what. Whoop. There we go. Thank you so much. Thank you all for your hard work. The two that are not here, we will hang on to them for a future time. And yeah, Chris, go ahead, show us how everybody, I'm sure more of you deserve these pins, and we'd love for you to show your hard work on Night Sky
Yeah,
Network as
so
well.
I downloaded all the volunteering hours, and yeah, I downloaded the volunteering hours from Night Sky Network, and we it looks like we probably, I would say, have another 15 to 20 people who, by the end of the year, if they carry on the way they're going, they'll get a pin. So let's talk about the volunteer hours. Next slide, please. So you log into Night Sky Network. You go to the event calendar, you click on the event at which you volunteered, and the event opens in a new browser window. So next slide. And you should see, like, this is me. So I put my volunteer hours for the executive board on July the 14th, and it's got a button there, add my volunteer hours. You click on that, and then a form will open for you to enter your hours. Now, I'll show you the form in a minute, but what if the event wasn't in the Night Sky Network calendar? Because sometimes the events don't get put in there. Okay, well, you log into Night Sky Network, but this time you don't go to the events, you hover over my profile and you'll see a drop-down menu, and you select my volunteer hours. And when my volunteer hours, that page comes up, you can add volunteer hours not related to an event. Click here, you click that link, and that gives you the form. So you can use two different ways of getting there. Next slide, please. And this is the form. So all you do is you fill it in. Don't forget to include your drive time in the hours, because it asks for miles driven. But if you've driven to a star party, we'd like you to also put in the amount of drive time there and back. Put that in, and because, well, that's it's all your time that you volunteered. So, any questions on that?
None here.
All right, very good. And I know Cy put me down as outreach chair in his earlier slide, but actually I'm going to hand that off to Michael. Michael Tier is going to be the
Yeah, I made a mistake.
guy for the board, and I'm going to transition to pick up where Peter left off, basically liaising with all the volunteers who work on IT related issues, whether it's the web design, the newsletter, social media, all that. And so there's going to be a little bit of change in the board responsibilities. All right, that's it. I finished. Thank you.
Thanks, Chris.
And Joe Christian, thank you.
That's all good stuff. Like I said, if you go to Star Party, put your miles in, but also include your drive time in the hours as well. So next slide then. Thanks, Christian. Thanks, Chris. Oh, there we go. It just shows how to do it, and I'll show you. This is a quick report of what's been done. Next slide. All right. Patrick, finally, you're up.
Alrighty, so here's our next star parties. I know I put this on the e-group the other day. So tomorrow night we got one in Mansfield for a rather recent community. This Saturday is the annual Space Day at the Museum of Science and History, where we'll have different vendors. We'll have tables. We'll have a table set up there. I'll be bringing the obsession as a display. We'll hand out some handouts and just basically promote our club. So if you want to help out with that, let me know, and I'll put more information about parking and when to set up and go up in the next couple of days. So on August 7th, we're going to be down in Granbury. Actually, 7th and 8th, it's going to be the same school. They're going to do a back-to-school day on the Saturday. I'm going to be down there for that, do solar viewing, but they also want a star party, so we'll do that on the Friday before. Next slide. Then, of course, August 8th will be our next Dinosaur Valley Star Party. And on the 14th will be at Wildflower. This is up towards the Texas Motor Speedway. We've been there a couple of times in the past. And then on the 15th, there's a back-to-school gathering. They want to do a little star party before they start school. It's kind of a smallest group, so I'll be there. Maybe just need like 1 or maybe 2 scopes, but I'll post all this on the e-group as we get closer. Thanks.
All right, next slide. Tiny Hills Outreach, John.
First off, I'd like to thank everybody that came out to our July Star Party. We had a great time. We had at least 11, maybe 12 members. Some of them are new members that I didn't know. Some were new members that I did know. 13 to 15 telescopes, including sea stars, dwarf lab minis, and just regular telescopes. Our next one is August 15th. Sun sets at about 8:15. We'll have two bright objects, I should say, Venus and Moon. We'll also have Pluto, as Bill mentioned in his presentation, but it'll be very dim and almost impossible to see. Even if it was not that much light, it'd still be hard to see. We'll also be catching the tail end of the Perseid meteor shower. And again, there's so much light out there, it's going to be really hard to see them unless we get a good fireball. So August 15th. And like I always like to say, with new members and people wanting to look at telescopes, trying to decide what kind of scope that they would like to have, we have them all. We're kind of like a used telescope lot. We have refractors, got reflectors, we've got mid-Cassegrain. So come out, take a test drive on those, see what you like, and we'll see you on August 15th.
All right, next slide. We'll skip this. Next slide. Next slide. 1687, next slide. We have nothing scheduled for right now. No current bookings. Hopefully in September we'll have something. Next slide. Paula Pinto, Michelle.
I have to thank everybody who's been out to work at the Palo Pinto Star Parties. We've only had 3 so far, so we're still getting our feet wet, but we've figured out pretty much how to get set up and make it easy. We have benefited the last couple of months since Dinosaur Valley has not had Star Party. A lot of those people have come out to Palo Pinto and helped out. So we've had anywhere from 15 to 20 scopes in an evening. Last week we only had maybe 30 in attendance. The month before that we had over 100 people attending the event, public. And these aren't people who just camp in the park. These are people coming from Abilene, Stephenville, and the Metroplex. And they're asking some really good questions. They've got a lot of good questions about astronomy. Our next one is scheduled for Saturday, August the 8th. I'll get that information out to you. One question that the ranger out there has asked, she's had some people who have voiced an interest in astrophotography, maybe doing an instructional class after the official Star Party ends. So if anybody has any way to help me with that, or if you want to volunteer to teach something along the lines of, we have several people who do EAA out there or who did this last time, but astrophotography to me is, you're talking about different filters that you use and all the detail stuff that we don't go into while we're just talking to the general public. So if you would like to help out with that, just let me know and we'll get that figured out.
Next slide. Michelle, you're back up. Tom.
Hi. So we've talked about the probably the afternoon or during the day on the 12th, possibly having a work party out at RSOA and then staying over for the Perseids. The defibrillator, I ran into some legal stuff, so I wrote up a finding and sent it to the committee. So we'll be looking at that, going through that, and then possibly setting up some training. So we're looking at that next few months, get that finished up. The mower video, Sam and I made a mower video a month or so ago. It turned out it was a gigabyte. It runs about 10 minutes, but it's a great video. I couldn't download it, so I sent it to George Lutch to see if we could put it on the file section of Groups.io, and he hasn't gotten back to me yet on that. So that should look for that. We're also going to set up 4 dates for parties out at Rising Star, October, December, March for the Messier, and then possibly in May. Our RSOA committee will discuss that, and we'll clear it by the board, and we'll get back to you on that. And then last but not least, as soon as I get the okay from Constantine, we'll change the codes.
Yes, if you don't pay your dues at the end of the month, codes will change. Next slide. Plains Library, no report on that yet. Next slide. Website media, George, you on?
I'm here, sir.
Yeah, you got it.
Just an apology to Tom Schneider. I did not see an email from you about the video. The only thing I got on there is about the training video for the lawnmower. Anyways, nothing major to go over with the media stuff. What I need to find out though is, and I guess it'll be up to me, is to find out how much space we actually have on groups.io. In case we want to put like the newsletter and stuff up into a directory on there. So if anybody knows offhand, throw it in an email to me. Otherwise, I'll go hunt it down. And that is it.
All right, thanks, George. Questions for George? None. Next. Bill.
Probably already read it, but we've got Dr. Renu Malhotra she's with University of Arizona, and she is a specialist in planetary migration, so how planets move orbitally through a solar system from beginning to the end of its movement.
All right. Next slide. Before we go to that, like I said, we have this Solar Observer's Handbook. If somebody wants to check it out to look at during next month and bring it back next meeting, that's fine. Our social hour at the Social House, 804 Curie Street, Fort Worth. A couple of us will go afterwards, after this, and have a drink and something to eat, but Constantine's got something.
Thank you. This is the second month that we've met in this room here. It's the first month that we've got the audio system working and everything. Everyone liking it? Terrific. Well, as of yesterday, UNT suggested we stay here the rest of the year. So unless there's objections, that's what we'll be doing. Thank you.
Great stuff. Anything else from anybody? I'll hear a motion to adjourn. All right, Christian, motion to adjourn. Do I hear a second? All right. I see Chris Modelicki. All in favor, say aye. All right, get out of here. Thanks for coming tonight.